Sure. Do I need to switch it on or it's already on? Okay, thanks. Thanks. Is this fine? The size is fine? Bigger. Maybe I should not write anyway if the crowd is on this side. I should not write on this side probably. Anyway, this will be the outline, so you won't have to look at it again and again.
Please use the table mic.
So we have 1 hour.
Yeah,
Slightly flexible.
For one and a half hour. You can start.
Hi everyone, welcome to the ICTS String seminar. So today we have Prithvi Narayan from IIT Palakkad. We'll be talking to us about double-scale DS-SYK.
Yeah, thanks Anupam. It's great to be back in ICTS after some time. Thanks Loga for inviting me over. I have been working on double-scale SYK initially and recently double-scale SYK, and I'm going to tell you a few things about it. So here is the outline of my talk. I'm going to tell you about the model and somewhat new combinatorial techniques to solve this model. I mean, this I assume all of you know something about SYK, so I won't give you much motivation. But this double-scale SYK is typically solved in a slightly different way than the usual SYK model, and I'll explain it. And what happens when you solve it is that there is a new effective Hamiltonian that one can write down after disorder averaging, and one can think of it some kind of dual Hamiltonian to the double-scale SYK model. Next, I'll quickly go over a recent work I have done, which is this is slightly old stuff now. Some generalizations that one can write down, and in the end, I'll comment on some connections to maybe not in the end, towards the later half of the talk. I'll talk about connections to the bulk, and the connection proceeds via some symmetries, quantum group symmetries. Okay, so let me start. So the Hamiltonian of the SYK model is given by some fermions interacting and some random disordered couplings. Okay, these are Majorana fermions. Chi's are Majorana fermions satisfying standard anti-commutation relation. J is a disorder. So you pick the couplings from some Gaussian ensemble, and constant here, which write down for the sake of completeness. It's best to, what I'm going to talk about is the double scaled SYK limit, and it's best to think of this index I1 to IP as some kind of combined index capital I, which is basically just set of ordered numbers. Take I1 to IP all different. That's how, that's your model. You take all the I1 to IP different. So this ordered set of numbers I'll together denote by this capital I. Okay, and this runs over n choose p indices in some sense. And then this whole product of fermions, I'll call it as some xi. Okay, and then together in a kind of short form, the way all these indices run from 1 to n. So in this compact notation, what we have is a JIXI kind of Hamiltonian, where xi is a product of fermions. Okay, now the double scale limit. The usual SYK limit is when you take n off to infinity, p being fixed. The original SYK was p equals to 4. You could also do it for different p's. People even do large p. But the double scale limit is a kind of a Tooft-like limit in some sense, where you take n off to infinity and p off to infinity such that p square by n, which is defined to be lambda, is fixed. And the model turns out to be solvable for all lambdas. What I mean when I say solvable, I'll tell you. But you can get some exact results in lambda. Of course, n goes to infinity, but you can get exact results in lambda. Okay, and one should think of the usual SYK model as the lambda going to 0 limit, because usual SYK is like p equals to 4 or small p. So it's more like a lambda going to 0 limit, and you will see that SYK results are kind of recovered in lambda going to 0 limit. In what sense also I'll say precisely. Sorry.
You don't need to scale J's.
No, J's are not scaled. I forgot to give the, so yeah, there is a specific way of writing down Ji, Jj. Okay, this is I forgot to tell it, but let me tell it. And this is like, let's say some number which I'll take 1, dimensional reason. And if you take this, you don't take a scaling of J. Yeah. This turns out to be the correct large n limit that you need to do. Roughly, you can see this by saying that, if you take h square, it's like Jij, and then Jij will be contracted by this. So that will give you a factor of 1 by n choose p, but there will also be a sum over i's. That will also go from 1 to n choose p. And there's only one index because Jij are contracted. So that's the correct scaling.
N choose p remains finite in this limit. If you keep p square by n fixed, n choose p becomes what? There'll be one term or something which will dominate.
No, n choose p goes off to infinity. Goes off to infinity, yeah.
I see. So, so you keep capital J fixed, but you...
Yes, capital J fixed. And n choose p, I won't say anything. It's just whatever happens. Yeah. It kind of disappears from the problem. Let me say that. Yeah. Okay. So that's the setup. Now I'm going to tell you how to solve the model. Let me see if I have something else to say. That's a disorder average. This is picked from an ensemble. You can take it to be Gaussian with this strength. Let me check whether I have to say something more in this general setup. Okay, I think that's all. Yeah. So next I'll talk about solving the model and the combinatorial technique that I mentioned. And to do that, it turns out that the appropriate object to look at is not partition function, but moments of Hamiltonian, which is basically this. Okay. You can think of it like a generating function. I mean, if you evaluate this for all k's and then sum it over, you can get a partition function. But this object turns out to be more basic. Yeah, there is no temperature. There's just you compute trace h to the power k. Yeah, that's a nice thing about this. Again, when I say I can get exact results, I can also get results exact in beta because yes. Yeah, I mean you can compute trace h to the power k explicitly and then you can sum it. Yeah. So this is what I will talk about. Let's just quickly see what happens for, let's say, trace for k equals to 2. Equals to 2, what happens is that you have two such objects, trace ji xi, trace ji xi, and then okay, maybe I'll look at trace x to the power 4. That's the kind of simplest non-trivial object. Suppose you were to compute this. What you have is something like this: ji, jj, jk, jl, 4 such disorder operators, disordered couplings, and then let me denote the double bracket here. This is the random average. You need to do this random average, and then you need to take a trace. xi, xj, xk, xl. Okay. And let me, since it's a trace, let me denote it by making a circle. And then you kind of think of this I, j, k, l as something on the circle. Okay. And then you need to sum over these I, j, k, l's. Okay. Now, this disorder averaging you do by a Gaussian contraction. So there are 4 terms when I equals to j, k equals to l, and I equals to k, j equals to l, and so on. So, sorry, there are 3 terms denoting 3 weak contractions. So let me denote these 3 terms by 3 diagrams. Like when I equals to j, let me draw it like this. K equals to L. This is that contraction. This is this contraction. And then there is one more like this. And then there is one cross contraction. Okay. So this I can graphically denote by this. Let me do the 3 calculations separately. Let's see what happens here. In this calculation, what you're supposed to do is just, this is just trace xi, xi, and then xj, xj. Okay. Along with some combinatorial factor of 1 by n choose p whole square. Also, there is some factor of i's which will disappear magically soon. And now you see that xi square, what is xi square? It's just chi I1 to chi IP, chi I1 to chi IP, and they square to 1. Each of these fermions square to 1. So this together, up to some minus signs which will actually cancel with this I to the power p. But you can see that xi square is just 1. Because you can get all the fermions together up to a cost of minus signs which will vanish because of this overall factor. and then this is 1. So this just gives me 1. And of course, there is also a sum over I, comma j, and that gives me an n choose p whole square, which cancels this n choose p whole square, and it's a finite number, just 1. If you keep track of normalizations. Okay, and similarly, the same thing happens here. This also becomes 1.
But the trace is...
Yes, yeah. So trace also you have to work with some normalization where trace is 1. Otherwise, you get some...
2 to the...
Yes, 2 to the power n by 2. Yeah, I'll work with the trace where it's 1. Trace of identity is 1. Okay, and this is also 1. Now, we come to this one. Now, this one, there's a small complication because what you're supposed to do is this is xi xj, xi xj. Now, if this j and I, sorry, these xi's were together, it would have been 1, but they're not together. So you have to flip it across this. And when you flip it, you will get as many minus signs as there are overlaps between I and j. I mean, there might be some common indices between I and j, in which case you don't get a minus sign. So net, relative to this 1, you get some extra factor of minus sign, which is depending on how much is the overlap between I and j indexes. Okay, and then after you do that flip, it's again 1 because xi square is 1, xj square is 1. So this, because there is also this 1 by n choose p whole square. This will basically be in some of our index sets I and j with the minus 1, and let me denote the number of overlaps by I intersection j. Okay. Now this turns out, so now this is like a simple combinatorial trick. If you take 2 index sets I and j, and then ask how many overlap, what's the probability? This one will give you a probability. Convert this sum into a probability. What is the probability of having some overlap? Let's say m. And there's some simple answer to it. Okay, so let me write it. So m is the overlap. Okay, and that can go from 0 to maximum, which is n, and then minus 1 to the power m, and then probability of I intersection j being m. Okay, so given any 2 index sets, what's the probability of having m overlaps between them? And then this is what you do. And then in the double scaling limit, you can evaluate this combinatorial problem. I mean, take 2 index sets with p indices each, and then ask how many overlaps are possible. And it turns out to be Poisson distributed. Okay. This probability turns out to be Poisson distributed. It's like lambda to the power m by m factorial divided by power minus lambda. And then you can do this infinite sum, and it just gives me, yeah, let me just do the sum. It gives me power minus 2 lambda. Yes, lambda is this coupling, which is held fixed. And this is the trick of the double scaling, that this number turns out to be finite. Okay, and if you are doing, like, for example, SYK, it would not matter because this would be a very small number. But this turns out to be finite. Okay, and then so net after all the dust settles, what you get for this diagram is e power minus 2 lambda. Now you can do the same calculation for higher point functions. Okay, and so the prescription turns out to be the following. Like if you were doing mk, trace h to the power k. What you do is you write down, oh, by the way, these are something called chord diagrams. Take a circle with some number of nodes in it and join it in all possible ways. These are something called chord diagrams, which mathematicians know about. And the prescription turns out to be the following. You sum over all possible chord diagrams with k nodes, all possible chord diagrams. And then for each chord diagram, the weight you associate, let's call this q, is q to the power number of intersections in that chord diagram. They give me 1. Yeah. You just count the number of intersections and then put a factor of q. Now, roughly you can see why it happens. I mean, not why it happens. Let me just tell you that's a fact. That what is happening is that you're kind of disentangling the chord diagram by taking this across. Right? That's what you're doing. This is xi, this is xj. Then you're disentangling. And it turns out that in the double scaling limit, the disentangling can be done independently of any other chord intersections. So that's just a fact of double scaling limit. And if you take that fact, then it becomes kind of obvious why all these intersections should give you an independent number that gives you a factor of q.
Can you do this exactly without the double scaling to sum?
Not as I know of, but there are some attempts at doing it at first subleading order in 1 by n. That also turns out to be kind of complicated. So, yeah.
But the explicit expression is no probability of.
Yeah, this one I think you can maybe do it, but the question is for higher point functions that that will become too complicated. Interacting, yeah, it will become some kind of interaction between vertices. Yeah.
But this is sort of like the genus 0 kind of, I mean, if you wish, in that sense, like the genus. So that.
Yeah, if you think of n as a quantum.
Higher, this analog of 1 over n suppression, and those other terms are kind of probably away from in the double scaling limit. There's usually some parameter that's fixed, and then there's a kind of a genus expansion like parameter.
I mean, here or in general, double scaling? Yeah, right,
so,
right.
And presumably those subleading ones are the analog of that kind of genus, like expansion.
Yeah, I don't know how much to push that analogy. I mean, yeah, whether n controls genus corrections.
The approximation that you make here, at least for the 4-point function, is that you are kind of going until only n.
N.
So
right.
It's not quite e to the minus 2 lambda, but it's for minus 2 lambda minus some tail in the Poisson distribution.
Right. I would think so.
After n, it's the probability that you will, find more than n particles in the Poisson distribution.
No, I think n will not work. I mean, yeah, this fixed number at n.
Yeah,
so this will not be true for all possible values.
So what I'm saying that the approximation you're doing is kind of, taking out some alternating sum in the Poisson thing.
Not only that, that's one, I think.
In this 4-point.
In this 4-point function, but even there, this probability, I think it reduces to Poisson the double scaling limit. There's
this formula you can directly
combinatorial formula which is there in general.
This you can give an exact formula for. It's like, choose P, choose M, and something. Yeah, that you can. P choose M, and then left over n minus p, you can choose it in p minus n base, and then divided by a probability which then choose p.
So this will have correction.
Yeah, this will have correction. That is one, and then there is another in which you stop here at n. That's another, and of
course probably like a finite effect kind of thing. But then there is what you said that if you look at higher diagrams, the fact that you can't disentangle these chords independently, that gives a further correction.
That I think is a much more complicated object too.
But is it fair in some sense to think of, so you'll evaluate everything in the strict double scaling limit and you'll get as a function of lambda or q. But can that expression be thought of as like the genus 0 or the tree level kind of an answer of whatever the dual theory you're considering?
Yeah, I think you can think of it like that, like all derivative corrections, all derivative corrections sum together.
But that kind of genus 0 without. I mean, presumably, you're studying this because then there's a dual gravity theory or string theory, whatever,
right.
And the quantum effects of that theory would be captured by the subleading corrections here.
Yeah, I think that's possible, but I would not push it too much because I would say that I don't know how much to go beyond n here, but ultimately here, maybe I'll say some picture. And that you probably can think of independently of this. Can I just quantize that picture? Yeah, maybe the short answer is I don't know. Yeah. What you're saying is true if you can think of lambda as derivative corrections and n as quantum corrections. I don't know if that's true or not. Yeah. Okay. So this is the prescription at the end of the day.
Well, it may not be n, it might be 2 to the n.
That is another thing, I guess, because
isn't that the kind of thing
Hilbert.
that, yeah, isn't that what determines the size of the Hilbert space, and therefore like e to the minus s naught is typically the kind of quantum corrections that you have in all this SYK stuff, right?
That's
so.
Yeah, that's as well as e power minus n.
It's a question of what the corrections are in terms of how does it. So my zeroth order question is there an analog of a genus expansion? If there is, what is the parameter that controls that expansion? Would it be n? Would it be 2 to the n? If at all if there's a genus expansion, presumably one parameter that controls the quantum effects.
If just from here, like if he's getting partial distribution by Stirling approximating binomial coefficients, then you would get probably 1 by n.
You would get 1 by n. I think there is also e power minus n maybe.
Yeah, this approximation seems to have 1 by n correction.
Right, but again, it's always a question of what you hold fixed. I mean, there might be things that will be subdominant. What is the systematic expansion parameter?
Yeah.
Multiply would be, if you can do it, multiply by some function of.
Yeah, if you can do it, yes.
It's not so obvious to see that. Yeah, I don't think it might be even 1 by n. It might be 2 to the n, because that's the size of the traces are what govern the non-planar corrections, and the higher corrections, presumably it will be the trace structure that will probably dominate it. Or maybe those correspond to, maybe.
No, I think 1 by n corrections, there are some efforts.
Yeah, there are
literally 1 by n
things.
corrections.
You could have considered moments, other moments, like trace h to the k1, trace h to the k2, trace h to the k3. Right. Then those will have a suppression, the connected pieces of that will have suppressions which are probably governed by 2 to the n.
Right. That there are some computations of ZZ expectation values.
Yes, so
that's Mika. No, it doesn't factorize. Yeah.
It should factorize in large n.
Yeah, large n it factorizes. That's true. Sorry. Yeah. When I said but there are Mika and Bakus and other people have computed trace kind of correlation functions. Yeah.
Then you can compute trace of e to the minus beta h.
Yes. Right.
You do have a finite temperature expansion.
Right. That's true. Yeah. So let me tell you how to do this sum. Well, I'll not tell how to do this sum. That actually has been done. Mathematicians know how to do it. But what I will do is I'll kind of give a different picture for it, which is actually, I think, in my opinion, more useful than the final answer itself. Okay, what I will do is I will give a kind of alternate way of thinking about it, in which you can think of this as an expectation value of some operator t, okay, on some Hilbert space state 0. Okay, and these are some very explicit state I'll give, and these are some very explicit matrices I'll give, and I'll tell you how this comes about. But it's kind of now obvious that if this is true, you can just exponentiate it. Exponentiating at left hand side will just give me an exponential e power minus beta t, and you can think of this t as a effective Hamiltonian for the SYK and double scale SYK. Okay. Yeah, it's a transfer matrix. Yeah, that's why I denoted by t. Okay, so let me tell you what the trick is. The trick is to kind of organize the calculation of this in a slightly different way. The way you can think of is that you kind of start building the chord diagram node by node. Okay, so first let's say you just had one node, And then the only thing that can happen is a chord can come out. That's the stage 1. And at second stage, what you could do is this chord either closes or there are 2 chords opening up. Okay, and this is the second stage. And then the third stage is, another chord can open up. Take this diagram. The only thing that can happen is that another chord can open up. Or in this diagram, there are 2 options. This chord or this chord closes or another chord opens up. So this can happen or this can happen. Stage 2, stage 3. Okay. So let me just do one more and then I'll say something. So at the next level, you can close this chord. Now you can kind of see that calculation just splits into 2 parts. Like once you see this, just one chord coming, it doesn't matter what is the previous history of it. The only thing is that what does that one chord do? Okay, that can either close or another chord can open up. Similarly, then all these 3 kind of behave similarly as far as future evolution is concerned. And that's the important point. So let me just do one more thing. Let's say I look at only those diagrams which have no loose chords hanging, and then this is the option. This one does not give that option. This one can give me this. Okay. And then there are more diagrams in which there is 2 open chords hanging. For example, you could open a chord here, something. Okay. So now, and when you think of, imagine like calculating the partial contribution of all these diagrams. Like, here there is no chord crossing, so 1, 1. Here it is 1, here it is Q, here, here there is no Q. So all these 3 diagrams will get 1, there's no Q, and so on. Okay. And for example, if you were to compute trace h to the power 4, what would do? We would say stop at the 4th stage, look at the diagrams which don't have any loose chord hanging around, and then just stop it. That would be the prescription. Okay, so that's the answer. Now, as I was telling you, the future evolution of this is just determined by what is the open chord structure. Like all these 3 diagrams behave similarly as far as future evolution is concerned. So this, in some sense, is the complete information that you need. Okay, so let me say VIL is the I is the ith stage, and L is number of open chords. Okay, and you compute this number. Okay, at ith stage with L open chords, what is the total contribution? For example, if you look at I equal to 3, V3, and then with 1 open chords, there is this diagram, this diagram, this diagram. This is 1, 1. This is Q. So, for example, third stage 1 open chord is just 2 plus Q. And third stage 3 open chords is just 1, because that's just this guy. Okay. Now, what I'm going to claim is like this is the total information about the state, is VIL. Once you give me VIL, I can write down a recursion relation which produces VI plus 1L. Okay, and the reason you can do that is the following. Let's say there is some number of chords happening, and then you start with you put an extra node. You could ask what happens. You could just get another node, get another chord, open chord. Okay, we can take a convention where we just freshly open chords are always on the bottom. Or another option that could do is that any one of these chord closes. Let's say this chord closes. That's another option. Or any other of these chords will close. Like, maybe not this one will just continue, but this one closes. Okay. But you can count all this. This guy just use another open chord. This guy gives you, the net result is the same. The only thing is that this gives me Q, or this gives me 1, this gives me Q square all the way till number L open chords. Okay. So let me just write down the recursion relation. Hopefully it will be obvious. if you have at I plus 1th stage L open chords, you can get it in two ways. One way is that you start with at the ith stage, you start with L minus 1 chords and just open one. Or at ith stage, you start with L plus 1, but close one. But when you close one, you have an option of which one you close, and all of them sum up 1, Q, and it doesn't matter which one happens, which process happens, it doesn't matter. For all future evaluation, the only thing relevant is that there are L open chords. L plus 1. Sorry. Bigger, okay. Yeah, there are L plus 1 chords, sorry, LL, sorry. Okay, and then this is the transfer matrix, and that's it. You can just get, now you can imagine this like a matrix. Now, for example, you can write it as Vi plus 1 is like T acting on Vi, where T is a matrix given by 0 on the diagonal, because there is no, from L open chords, you cannot get another L open chord. 1 below the diagonal, 0 everywhere else, and above the diagonal, let's call this eta L plus 1. This is like a Q number. Now you start seeing Qs happening. Like if your Q was 1, this was L plus 1. And then I think the standard notation is plus 1 Q. But anyway, I'll call it eta. That's what we've been calling it. And then on the upper diagonal, it is eta 0, eta 1. Okay. So this is the T matrix. Yeah.
Perhaps you said this one. Why do you ignore the diagrams with no open chords?
No open chords, it doesn't, I don't ignore it. I just said that like if you want to compute trace h to the power 4, what you need to do in this procedure is go to 4th stage, forget about all the diagrams which have one open chords, because they are not relevant. You only look at diagrams which are like these three, for example, are exactly what we did, right? I mean, trace h to the power 4, you get this. These three are these three. Okay. So this is the transfer matrix. And now there is just one more thing. How am I going to get trace h to the power k as expectation value? What you need to do is just stop this process at the kth stage, and k is like kth stage. You stop the process and you pick out the number of, pick out the contribution from diagrams with no open chords, Vk0. Okay. And this is just, Vk is just T acting on V0, T acting on Vi minus 1, Vk minus 1, which itself is T acting on Vk minus 2, and so on. So T to the power k times V0. And V0 is just like where you start. This is the first stage, but you could in principle take a 0th stage, which is just 1, 0, 0, 0, 0. This is V0th stage, where this is just a convention one can take. And this is that column vector, 1, 0, 0 column vector. You compute this, take the kth action of T on it, and then to get Vk0, what you can do is just take V0 transpose, because that just picks out the V0 is just the 1, 0, 0, 0. So if you take a transpose with V0 and multiply it, you just pick out the first L equal to 0 component of this vector. So this is what it is. Okay. So now I can finally, this 1, 0, 0. Well, I mean, this is just this, like for example, V1, let me just write down, maybe I didn't say it explicitly, VIL is a column vector, right? L is I is the ith stage and L is the label of the row. So for example, V10 is like, there is no diagrams with 0 open chords. There is one diagram with contribution 1 with 1 open chord and 0 and so on. And here at second stage, what you have is there is one diagram with 0 open chords, L equal to 0. There are no diagrams with 1 open chord, 0. And there is one diagram with 2 open chords. So this is L equal to 0, L equal to 1, L equal to 2. So this, you construct this column vector at each stage. And you stop at kth stage, look at the first number, and that is your trace h to the power k. And the way you obtain it is that you start from V1. By the way, if you act upon this by t, you get this, because that's how we write. So we get take t, you get this, and so on and so forth. So, yeah, this is the prescription.
Basically, the point is that just try to
You
start with the partition function of the SYK.
Okay. Okay.
So you expand it, you sum over all the disorder completely.
Okay.
Then you rewrite that model in terms of new basically or a transform.
Right.
So that's correct.
Right. Yeah. Although the procedure doesn't involve partition function, but mostly moments of h. But yeah, that's figuratively what's happening.
In this particular limit itself.
Yeah, right. So again, let me just reiterate. This 0 is just 1, 0, 0 column vector, and T is that matrix that I wrote down. Okay, so after all the dust settles down, this is what the answer is. And now, hopefully, it's now obvious that you. Right. This is the
number of states. Next.
Right. Right. This. So, in some sense, what you're doing is like, okay. So when I say I do this chord diagram like this, what I'm imagining is I'm cutting the chord diagram somewhere, flattening it out, and then evolving. So what T does is T. This is like, you can think of it like a thermal circle, and T evolves along the circle, and then you do all the things like, chords. Some chord evolution happens, and then you come back and project to the state where there is no chords, because of course you have to close the circle. So this is like an evolution on this side. This is more like a one-sided evolution in some sense. Now there are other attempts, like I think you were saying that Almari was giving a talk last time, and also Henry Lin. So these people kind of want to think about this like a two-sided evolution. They want to, they have the same calculation, but they want to interpret it like two-sided evolution. Two-sided black hole, if you want. We don't have that. At least the way I constructed it explicitly, it's like evolution like this. That seems to be what we are getting. I don't have much to say. We have read those papers. I don't have much to say about what they do. But the calculations are exactly the same. There is no difference in the calculation. It's just this original calculation. It's a question of interpretation. Whether we talk about one state here, they talk about double states. So, yeah. Okay, so I think I'm running out of time here, but let me just, because I also want to talk about the last part of things, which is, this generalization is not such a big deal, but the quantum groups I do want to talk about. Anyway, so this is the dual Hamiltonian, and you can do all sorts of things now. For example, you can literally think of it like a dual partition function, dual Hamiltonian, because, for example, e power minus beta h is just 0 e power minus beta t. Let me tell you a few things about this T matrix. Okay, so one thing, this is just an aside, is that okay, this is not Hermitian, but you can easily make it Hermitian by doing some multiplication of some some conjugation, right? So let me call that T hat, and that turns out to be slightly better because it's Hermitian. It's just the same factor, but square roots here. Okay, just a simple conjugation which deals with this. But now you can, sorry?
You're saying that you can actually act,
yeah, you can just multiply by, you can write down some operator P where P hat, yeah, anyway. Sorry?
There's some S and then P is P hat S.
Right. Yeah.
Or is it S P hat S inverse or S transpose P hat?
S transpose, because it's not a similarity transformation. The eigenvalues change.
So it's S transpose.
No, eigenvalues don't change, eigenvectors. Vectors change, yeah.
So S transpose T hat S. Can you just
S transpose T hat S, yes.
T is S hat.
So I'll have to figure out what it is, but yeah, it's roughly like that. Yeah. T hat is S hat transpose. S hat happens to be diagonal, so it doesn't matter. So S hat T S hat. Yeah, that's right. And S hat is not squares to one. It's not. This is a diagonal matrix. I mean, you can kind of see why it's happening, because I'm actually evolving the thing on the right. So I'm explicitly kind of breaking the left-right symmetry in some sense. Because when I add a node, I'm not adding any factor, I'm just putting it below. Anyway, so yeah, it's a diagonal matrix.
So I can write the other way around.
Yeah. There's no loss of information, anything. In fact, it's very simple. I mean, it'll probably take 2 minutes to write this down. Okay, let me just make a comment here. This, as I was telling you, eta is like if you take q goes to 1, eta is just number, right? I mean, eta is just L. For q goes to 1. Now you can see what this is. This is square roots. And this structure is exactly like an A plus A dagger. A harmonic oscillator. If you take harmonic oscillator, A is exactly this with this, well, one of these, I mean, I think this one, yeah. And A dagger is this one. So this is like an A plus A dagger, which is basically like an X of a harmonic oscillator. Now it turns out that this object can be written as AQ plus AQ dagger, where AQ is this matrix, where instead of root L, I have eta L, root eta L. And then this satisfies some nice commutation relation. AQ dagger minus Q times AQ dagger AQ is 1 structure. Okay. Sorry, I'm not, this is just a side throwaway comment. So it's just a Q deformation of the harmonic oscillator algebra. And here is the first time where you are seeing that what we are doing, although looks like a combinatorial technique, finally, after the dust settles down, there is some nice Q deformation interpretation to it. Okay. And we will come back to that later on. Okay. This is just a side comment. We have not been able to make use of this much. But that's one connection to Q deformation. Second thing I wanted to mention is that this T is there's an explicit map.
I just want to make a remark that the Q goes to 0 limit of this, not the Q goes to 1. The Q goes to 0 limit is actually the thing that counts planar diagrams. And this is known as the Kunz algebra.
Yes, actually you can see why you remember this was the...
No, I know.
Yeah, sure.
This thing, but that algebra has made its appearance. And recently people who, there's this whole mathematical machinery of free probability theory.
Right.
And this is sort of the beginning of that. And it has a very natural mathematical meaning as the sort of the large N master field corresponding to the matrix, the original matrix integral. So the kind of these operators are really, if you wish, this Hilbert space that you've constructed, the operator T that you've constructed, are in some sense what you might call the master field for that. I see. For this model, at least in the Q goes to 0 limit. But I think there are generalizations. There's this Xinjiao Wang. I don't know if you've seen his papers. There's a postdoc at Stanford. He has been studying this it has relations to quantum information also. And
actually, Berku's one of the collaborators are actually, they are thinking about these free probabilities. I don't know what they're doing. I mean, I didn't pursue that angle.
Xinjiao Wang has has made it explicit.
Made it explicit. Okay, yeah. There's also some relation to quantum Brownian motion, something. Yeah, I don't know much about that literature. Yeah, there is some stochastic people who also think about these things. Yeah.
Strictly speaking, you can't quite take a small equilibrium.
Sorry?
Strictly speaking,
Huh.
we can't quite take a small equilibrium because it's like large lambda, which will make p greater than it. But
It's okay, you can take it. Q goes to one limit. Sorry, Q goes to 0 limit is lambda goes to infinity limit. It's okay. I mean, you can control it. That's always true, but n is always the biggest parameter in the game.
Square is much larger.
Yeah, but you can make p square by n as big as you want. I mean, n being still the largest number, you can still take lambda up to infinity. Okay. Q is e power minus 2 lambda. Maybe you should write it somewhere. So one more thing was that you could, this is a very explicit matrix and you can compute the spectrum of it. So if you know the spectrum, it's very easy to evaluate this object. This guy is just, or maybe just e power minus beta t, which is the partition function. Is just, let's call the eigenvalues of t, spectrum of t as e. And then this would be dE 0 E squared and then for minus beta E. And then there is the measure factor for E that will also be there, but it turns out that there is nothing here. And then this has the interpretation of the density of states. Okay, of the SYK model, the double scale SYK model. So the point to note is that this is not the density of states of this T matrix. It's more like the wave function of that. That is what enters the density of states of the SYK. But so now I'll just make a comment about the connection to the SYK. Sorry, yes, there are some very explicit expressions for this, but it is, yeah, it's ugly. Huh? I can write it down, but it's very ugly.
Sorry, later on.
Yeah. I mean, there are explicit expressions in the paper. So, I mean, that actually was also known before. Even without this, this density of states of double scaled SYK was worked out by this Schenker, Stanford, Polchinski, that big 80-page paper. Anyway, so you can take a lambda going to 0 limit and low energy limit. Okay, how to take? You have to scale E with. You have to, the row of E has some. No. This is the row of E. This is supposed to be like a. Okay, fine. Anyway, now if you take lambda going to 0 along with the low energy limit, which basically means focus on this edge, then you get this sinh function. Sinh square root E kind of function. E minus E naught is, let's say, is the left edge. And that's the same as SYK, Schwarzian density of states. That's one kind of connection you can draw. Another connection, which is slightly more explicit, is the.
Because 0 limit becomes the vector.
Yes, if you take literally, sorry, Q goes to 0 limit. Yeah, right. Q goes to 0 limit, it becomes Wigner semicircle, that's correct. Q goes to 1 limit if you just take without, this is lambda going to 0 is Q goes to 1. And if you don't take the low energy limit, it just becomes a Gaussian. But if you zoom in on the low energy, then you get this sinh function. Sorry? Yeah, I'm just roughly E minus E naught. E naught is the lowest energy. E minus E naught is the deviations from the lowest energy. And then there are some factors of lambdas hanging around, which I'm not writing now, but it matches. You have to take appropriate matchings, just matches. That's one thing. Another thing I wanted to comment is, that's A, is that there is another similarity transformation you can do of this, which makes it a little bit, which is useful for this purpose, which is, let me call it T tilde or something. So then you can do 0, 0, 0, 0. And then you can take a similarity transformation And this is something like this, 1 minus q by 1 minus q, 1 minus, sorry, maybe 1 minus q is not there outside. Let me just. Something like this. 1 minus q squared, 1 minus q to the power I. Okay, again, let me just be slightly qualitative here. So this is another similarity transformation, maybe minus of that. Okay, and the point is that far down here, let's say, and q is by the way smaller than 1 always, because q is e power minus 2 lambda, it's always smaller than 1. So this guy becomes 1, because q to the power I becomes 0 because I is very far down the line. So this matrix looks like this. I mean, let me forget about the factors overall. 0, 0, 0, 0, 0, minus 1, minus 1, minus 1. Now this is just a discrete version of this L square operator. Derivative, double derivative operator. Okay, plus 2, because you have to make it 2 diagonal.
1D lattice.
Yeah, it's a 1D lattice version. Now you could ask what happens if there is q to the power I, and then it turns out that what you need to do is just add, let's say you work with some kind of discrete, continuous variables, in the sense that we want to work with lambda goes to 0 limit. So let's say I lambda is well, q to the power I is e power 5. It's easier probably. Okay, this is,
This is the ladder with infinity.
No, q to the, I'm going far down this. It's like roughly like low energy limit. Okay. And then this q to the power I is e power 5, and you can think, if you take lambda going to 0 limit, you can think of phi as a continuous variable, and that's the limit in which this becomes del square. And in that same limit, q to the power I becomes e power 5. So this becomes like something like this. Okay, and the Hamiltonian, this is a Liouville theory. Okay, this is a Liouville Hamiltonian, Liouville quantum mechanics. And it turns out that this is the best, sorry, saying something. Yeah, it turns out that this is the best picture that one can, at least what we could think, that our whole process is like a q-deformation of this picture. This is qualitative. I'll probably say something more concrete.
Can I ask a couple of questions?
Yeah, sure.
First question is something I didn't understand. You're inventing, so you found a formula for T.
Yes.
Then you're inventing similarity transformations.
Right.
And then you're looking at the partition function of those new transformations.
Yeah, partition function is the same.
So what are you doing?
Yeah, all these similarity transformations don't affect the 0 state. Maybe I should not have, I should have said that. S hat acting on 0 is 0. So it's the same partition.
Is the physics different?
I think not. I think it's a question of what inner product you assign to the states. I think it's not. Yeah.
My question. Is the physics different in the sense that are these two different partition functions in some sense?
No, the partition functions are exactly same. That's just a mathematical statement, because this is just 0 t hat to the power k 0. Partition functions are exactly the same. So you still get e power minus beta t hat, e power minus beta t, all these things, it doesn't matter.
So then you can then take different limits better, or what is the reason to do this?
Yeah, some aspects become clearer in some.
This makes it, the original form was not self-adjoint.
This was not self-adjoint, yeah. I think there is a preferred. Maybe this is the preferred one, let's say. This is like a Hamiltonian, proper Hamiltonian, because it's a symmetric Hermitian matrix. In some sense, this is the preferred one. But for some other things, something else might be more useful. For example, I think even in this, one could make an argument that it is Liouville. It's just a question. The details are not so obvious. Here it's becoming almost obvious because this is q to the power I literally becomes e power 5. I think it's a, yeah.
So this about the shouldn't you get like S square, SX square factors?
In between here? Right. Let me just think. Yeah, you're right. You're right. But I'm not seeing why exactly that's not the case. Is just saying that there are some factors of S is missing here.
Yeah, so the DS on either side, that's all.
No, because each T itself is S T hat S.
The S inverse.
S inverse or S transpose is the question.
S inverse.
S inverse. Yeah, I can just look it up. Yeah, no, forgot. Sorry about this. Yeah, let me see if I have an explicit.
S0 is 0.
Yeah.
S0 is 0 also.
Yeah, I don't have it. Yeah, I don't have it here, but yeah, I think the final answer is the same. That might be, yeah, I might have messed up whether it is S transpose or S inverse.
It can't be S transpose.
Yeah, I think it might be S inverse.
Because S transpose will take a Hessian matrix only to a non-Hessian matrix.
Right. Yeah, I'm sorry about this. I don't remember, but I mean, I don't think there's an algebraic error here. It's just true. I'm just not able to remember what S hat, whether it's a set transpose or a set. I think it must be a set inverse. Yeah, that's probably straight.
If you do this particular Schwarzian transformation, then this you will go QM emerges. But you should be able to see this there also.
Yeah, you can do it. You can do it there also. It's more difficult. That's all. Okay, so now what? Okay, yeah.
So if you take S-SYK model,
Right.
the standard one, and you massage it appropriately, you can get the representation of the Schwarzian in terms of the Liouville theory, modulo some important boundary condition.
Right.
You can do that actually, that way, and it's a pretty cheap way of doing it,
Right.
rather than this very sophisticated. What do I gain from it?
The gain is that there is an exact deformation of this. It's like a one parameter exact deformation of that story, which describes the full DS-SYK at all energies. By the way, the Schwarzian is a low energy theory.
That is fine. Okay.
You get two things. You get all energies and you get a one parameter deformation of that story. Right. And yeah, as Spenta was saying, I mean, I stopped here at Liouville, but there is some rewriting of Liouville up to some subtleties as the Schwarzian theory. Okay. And the subtleties are something to do with the boundary conditions. But I think people kind of think of Liouville and Schwarzian in an equivalent way. Okay. So that picture is what's probably most important to what I'm going to tell next. Okay. So this is where I will stop this part because I really want to, so maybe some 15-20 minutes. Can I take a next? Yeah, is that fine? Yeah. Sorry. Now you could ask what else one can do with it. Let me tell you one thing that I did, which was, this was done more recently. We could, as you might know, SYK has a lot of variants. Okay, there are a lot of like supersymmetric versions of SYK, global symmetric versions. You could take as SYKs and couple it. Now you could ask what's the double scaling limit of all these models? I mean, does it make sense to ask about the double scaling limit of all these models? And some questions have been answered. For example, the supersymmetric SYK Barkos and collaborators did it. There are also attempts at doing complex SYK in the double scaling limit. So what happens there? It turns out the best. Let me not write it here. The Hamiltonian. It turns out that if you take this kind of Hamiltonian, where chi's are still the fermion products, chi daggers are the same fermion products, but dagger. Now they are not Majorana fermion; they are complex fermions. You could take this SYK model, SYK complex SYK model, and you could run through the double scaling story, and you almost get exactly the same answer. Okay, so this is what we pushed it a little bit more further in recent work. So what we kind of saw was that what happens if you start putting indices on this. Okay, so let's say you take something like this, A, B are some kind of flavor indices. Let's call these i's which ran from 1 to n as color. Okay, and then this capital A, which is made out of small a indices, let's call it flavor. Start putting these things. And this A is actually just A1 to AP. I is I1 to IP. And what I mean by this is X IA is just chi I1 A1. Something like this. Okay, and then to soak up these indices, you could also have an kind of invariant tensor of the group. I mean, I'm having in in the backdrop, I'm thinking that this ones form some flavor symmetry, like depending on SAB, it could be UM or SOM or SP. So any kind of classical groups is possible. Probably even some more fancier other groups are also possible. But it doesn't matter what, I can give some general expressions directly in terms of S. And then we worked through the double scaled procedure and kind of got the same results. Okay, so let me just quickly tell what happens. The only complication now is that now chord diagrams, there are two complications. One is that one chord diagram, you remember, was an XX kind of contraction. Now each Hamiltonian is not just one X, there are two X's. So it's like one chord splitting into two. So it's like you have a more like an oriented chords. Okay, so same picture, but now oriented chords. And then with this AB, CD, and then there is an SAB, SCD. So it's just the same thing, but with more indices hanging around. Okay. Now the chord diagram techniques can also be pushed, and let me just finally tell the answer. If you remember that the chord diagram contribution, like MK was just chord diagram, some or all chord diagrams, then q to the power number of crossings. Right? That was the original story. Now it turns out that this has to be replaced with the following, that if you see a pair of, okay, first of all, this oriented chords turns out to be a kind of not so important thing. What you can do is replace this oriented chords with some kind of thick chords. Let me say, okay, this is the same, maybe I'll call it a wavy line or something. Okay. So it turns out that the chord diagrams are now written in terms of these wavy chords. Okay. And then this picture kind of changes. What happens is that anytime you have a nested wavy chord, you get some factor. Let's call it e power lambda or nested. And every time you have a crossing wavy chord, you get another factor, e power lambda c. Okay. So that's the prescription. Sorry, e power minus lambda and lambda c. No, it doesn't matter, it's just a definition. I haven't told you what lambda n and lambda c is. And what lambda n and lambda c turns out is some kind of lambda c or lambda n, I'm not going to give an explicit expression, is some kind of four trace, four fermion traces, something like this. Okay. And this trace is in the flavor index. It's something like this: A, B, C, D, trace chi chi. Then there are some details here. I mean, I'm not telling these explicitly, but this is the rough structure. The point is that you don't have to tell anything about what SABs are. Okay, these are all just, there is some number that you can compute for any given SAB. You can compute that number. That number sits here. These are the rules. Okay. Now you might think this is totally different from. Okay, by the way you go back to kind of the original SYK is that this lambda n becomes 0 if you take the original SYK, because the original SYK is also, you can think of that also in this setup. And then lambda n becomes 0, you only have lambda c, which is exactly what we had. But the new ingredient is that all the nested chords, not just crossing, also gets a factor. Okay, and now at this point, I don't want to say too much about this. Many of these stories go ahead. But also there is one thing that some number times k square, you get another new ingredient here, which is k square times some number, not just whatever it was here. And this kind of, and by the way, we can do it with chemical potential also. Could have some chemical potential. Just all these traces have an extra insertion of chemical potential. That's also there. So this spoils the party, because when you do the partition function, you have to sum over k, you remember? Sum over k with beta to the power k by k factorial kind of thing. This one doesn't converge. So one doesn't know what to do with it. So that's one kind of a problem. If you turn off all the chemical potentials, this won't be there. This number becomes 0 if you turn off chemical potentials. But if you keep the chemical potential, it's non-zero and we don't know how to sum it. That's one thing. Another nice mathematical structure that turns out is that you could do the transfer matrix for this. Theta function? Theta, Hughes-side theta? Step.
It's like some exponent, it's like something to the power k. It's like some exponent of some quadratic polynomial over integers. Is some function.
I didn't get what you're saying.
See, sum over e to the power n. Sum over x to the power n. This is 1 by x to the power. It's a geometric series. It's
okay.
But there's also some function which is described sum over x power n plus n square, a n plus e n square.
Mm-hmm.
You're
saying that.
That's what I said. So the point is that like you can.
No, I'm yeah.
Subtract out some.
Maybe I'll talk to you about this later. I don't know. And you have to have a 1 by k factorial and sum it, and that should converge. So maybe I'll talk to you about this later if there is a nice way of doing it. We couldn't do it. One another thing I wanted to comment is that you could ask how the transfer matrix picture changes. And it turns out that it's almost the same, except that this eta L, which was 1 minus q to the power L divided by 1 minus q to the power 1 minus q, this changes. Actually, what you will get is q, let's call it qn to the power L divided by qn minus q. If this you call it to be q. This is q. Okay. So this is, and mathematicians also know about this. I mean, this is it's like a PQ deformation of a number. And yeah, so mathematicians also know about this. So this is just what we get ultimately is the same transfer matrix, but with that eta replaced with this. Now, unfortunately, mathematicians don't tell us how to diagonalize this. I mean, there is no explicit formulas known for spectrum of this. So yeah, so that's another loose end. Okay, so let me just stop here and I want to go to this last topic. And again, I'll be sketchy here because quantum groups are good. These are very long expressions. But let me tell you some story about the bulk. Okay, now you could ask what does all this nice thing? what do we do with this? Can we say something useful about bulk? And it turns out that, I don't know, which picture of bulk is important. So we are able to make connection to one particular picture of the bulk, and that's what I'm going to tell you. And this is the following, that you can think of Schwarzian, or maybe more precisely Liouville theory, as a particle moving on ADS3. Okay, so if you do a reduction, particle moving on ADS3, you get Liouville. Okay, what I mean by that, I'll make it precise. And then this picture can be q-deformed. That's what I'm going to say. And by the way, I didn't tell you one more thing, which was that this q-deformation, we kind of suspect this is due to the calculation of 4-point functions in this double-scaled SYK model. People have computed the 4-point functions of double-scaled SYK model. And it turns out that that 4-point function is the same as 6J symbol of some quantum group. Okay, and let me just write it down, which quantum group it is. It's called UQ SU1,1. SU1,1 is just SL2R. And then this is a quantum group deformation of it. And it turns out that whether it is SL2R or SU1,1 matters when you do the quantum deformation, Q deformation. So this is the quantum group which crops up when you start doing 4-point functions. In what sense, I'm not going to tell you, but this is the kind of picture that we are going to do. What we're going to do is some Q deformation of this, and we have an idea about what quantum group we should be looking at. So that's what I'm going to do. So let me just quickly tell you how this comes about. Okay, just in 5 minutes or so. So what you do is you first start with SL2C, and then you consider the manifold, or G is alpha, beta, gamma, delta, with alpha, delta minus beta, gamma is 1. I'm going to do mostly complex. I'm not going to do the real form yet. I mean, probably not even in the end. So this is my SL2C, and you could consider a coset space, homogeneous space built out of it, which is like this. If you take G dagger G, this lives in SL2C mod SU2, because if you do a left transformation of G with SU2, it's invariant. So X parameterizes a manifold which lives on SL2C mod SU2. Okay, and then you could write it in terms of alpha, beta, gamma, deltas, but then parameterize this manifold. There's a name for it, which is Lobachevsky space. Okay, and this basically it's the hyperbolic plane. Euclideanized. Yeah, that depends on whether it is which real form you take. But you could take if you take so there is both Lorentzian also and Euclidean also, whichever we want. And then you parameterize this by this object Hz, Z bar, H bar, and then this gets determined because this determinant is 1. So this gets determined, it's some complicated thing. So this H, Z, and Z bar are coordinates on this hyperbolic plane. Okay. Now, what you can do, now this SL2C symmetry of the original SL2C descends to the homogeneous space also. So you could write down generators. So maybe I'll just write it down, because I'm not going to say much about the quantum group. So here where the expressions are simple, I can just write it down. So you can do generators. So you can, for example, generator. So this is the usual symmetry, which is the scaling symmetry of ADS3. And then C is xz del H minus Z square del Z plus H inverse square del Z bar. Okay. And you can even write down the metric. H inverse square. Yeah, H square, sorry. This is a metric. You can find out the generators, the SL2C generators. There's also complex conjugates of this. And then you can do the Casimir also, which is something like L0 square plus BC. Sorry? L1 and L minus 1, but I like to call it as B and C for some quantum group regions. Yeah. Okay. Again, there are some factors here which I think there is some factor of 5, 2 here, some factor of 1 by 4. You can compute the quadratic Casimir of this and then ask the following question. What are the eigenfunctions of quadratic Casimir? Basically, if you have a particle moving on this ADS3 and its Hamiltonian is given by omega, what are its eigenvalues? So let's say you want to look at omega acting on psi, which is a function of h, z, and z bar, square psi, z and z bar. You want to solve this problem. Wave functions of particles moving on ADS2, okay, on this homogeneous space. Now, to solve this, it's useful to, since omega commutes with b, and b is just del z, you can go to eigenfunctions of z, eigenfunctions of b. These are just the one eigenfunctions which are diagonalizing del z, which are just exponentials. So if you take psi to be e power I mu z, let's call it psi tilde of h e power minus I mu z, maybe nu. You can take independent eigenfunctions on both sides. So let me just write the answer down. If you take this, let's call it mu bar maybe. Sorry. Again, mu and mu bar need not have specific relation. It depends on whether you're considering Euclidean or Lorentzian. But I'll just take mu and mu bar independent for now. And then what happens is the following. This equation for psi tilde becomes, if you have to redefine h, phi is like log h. Okay, and once you do that, you get this. Number times number will be related to this lambda square. But okay, is this fine? These are all the explicit expressions that I'm going to give you. Next time I'm going to say some things which are cannot write explicit expressions now because it's very complicated, but it's there in the paper that we wrote. Okay, is this fine? So here is a picture where you can start from ADS3 and land on Liouville quantum mechanics. And it turns out that this picture you can q-deform easily. And the reason that's possible is that everything is in terms of groups here. And you know what these groups are, like quantum deformations of the groups are. Okay, so let me just quickly say what happens. So first, there are various algebraic objects that you need. Okay, I'm sorry, I'm going to be slightly qualitative here, mainly because the expressions are complicated. I don't have time anyways, but also because expressions are so complicated, I cannot give it any in the real time. So first thing that you should do is define a q-deformation of SL2C. Okay, so that's the first object you need to define. Q-deformation of SL2C are this same kind of thing, but now beta, gamma, delta, alpha, beta, gamma, delta are non-commutative. Okay, and they satisfy some commutation relations. For example, just to give you one qualitative thing, alpha beta is like q to the power half beta alpha. And then there are lots of other commutation relations, 10 or 15 of them among all these alpha, beta, gamma, deltas. And for example, this guy also gets modified. it's a q to the power half here, and so on and so forth, a lot more. Okay, so this is a q deformation of SL2C. This is called functions on the group, generators of the functions on the group. So mathematicians know how to do quantum deformations of SL2C, and you can go to the math literature. This is what this whole procedure took us a long time. Although we knew qualitatively this had to happen, practically digging up the mathematical literature and penetrating it took us a long time. Okay, but anyway, this is somewhere there in all the q deformations of the SL2C functions on the group have been classified, and there are some ambiguities. Okay, these come with some parameters. Okay, and these parameters turn up here where when we write down the commutation relations, it's not uniquely determined. There are a few parameters worth of q deformations possible. That's one. That's one ingredient, one part of the story. Okay, and again, second part of the story is defining generators. Okay, so again, you have this B, C, and L0. Turns out you can q deform it. Yes, that's also there. Yeah. So all of these things have some mathematical subtleties associated with it, and I'm not sure that we addressed all of them, but I'll point out what subtleties we have not addressed. So this BCL0 can be q deformed. Okay, and again they satisfy some algebra. It turns out that the structure that this is this algebra, it actually satisfies a Hopf algebra. And similarly, these generators also satisfy a Hopf algebra. So there is a q deformed, and again there is it turns out that there is again a few parameter worth of q deformations. So let me put some dots here. A few parameters worth of it. So this is the second structure. Now the third structure is doing the coset construction. Again, you take the same thing, H to be this, and then HZ and Z bar parameterizes this L3. Now L3 will have a q deformation. Again, there will be parameters. So let me put dot here. There are some discrete parameters that you can choose. Well, not discrete continuous parameters, but okay. Anyway, so these are there. Now, what turns out is that now this H, Z, and Z bar don't commute. Okay, they are non-commutative. So H, Z, Z bar are non-commutative. Just to give you again one specific kind of commutation, just so that you feel that you saw some non-commutative geometry. These are some relation. Sorry. Yes. Yeah. So what is this L3Q? It's some object described by these coordinates, which are non-commutative, and things are under control because we know how generators act. Okay, so again, I didn't tell you, but there are some ways in which these generators act on these group elements. And once you know these group elements, since these H's are just determined in terms of these group elements, you know how the generators act on the coordinates H, Z, Z, Z. So you also know. So this is one ingredient that this H, Z. After all these dust settles, you don't have to go back to these SL2 deformations too much. The thing that you need to read is that there are some anti-commutation, nice commutation relations. Second thing is that you know how the generators act. So how these B, C generators act on functions of HG. Z bar, H, Z. Okay, these happen to be some discrete analogs of this. Okay. Right now, okay, so there are some subtleties which I'll point out, but these H and Z bar are some discrete objects now. Okay, that's not very. Yeah, what you can say is that all this becomes discrete. You jump with these generators, you jump on lattice of Z and H and H, Z bar, right? I mean, for example, let me just give you one, what happens to B, that's probably the most nice thing. So B acting on F, Z bar, H, Z. Now, again, Z, you remember Z bar, H and Z are non-commutative. So I'll have to tell how you have to do some normal ordering when I define this. Okay, so the normal ordering is like take all Z bars, multiply it, and then H's together and then Z's together. You are not allowed any other, and that's how you build your functions. Anyway, so that's how you do B.
Like some of these operators and some of these functions.
Mm-hmm.
The natural space that they're living on doesn't have, like a very simple topology. Is that what you're saying?
Simple topology. That's why I'm calling it as?
It has basically, like only discrete topology.
No, let me just say it. Discrete action, yeah. So let me just say what it is. This has a then Z, or Z, for example. What I mean by this is some kind of normal order. Yeah, it's a difference operator, right? So what happens here is that del C becomes a difference operator. It's like a q deformation of a, and of course you can check that if you take q goes to 1, it becomes del C. But this becomes a discrete difference operator. So all these generators kind of consistently act on a lattice of HQs. Okay, I haven't told you what other generators are, but they are roughly like this. Again, so they act on a lattice of H and Z. Sorry?
What lattice?
Lattice of H and Z.
Sorry.
H and Z. Like we can take H, Z, and Z bar to be living in some lattice. Q to the power. Okay, and well, this is now just a consistency thing. I mean, it's consistent to take it like that. What would be nice is, if there is, so there are, what would be nice is if there is a way of just, in mathematics, just this being the spectrum of operators, Z, H, and Z. Not.
What are you saying? You told us about the transfer matrix. You told us about perhaps also the Hilbert space of each blank.
Mm-hmm.
Is this connected to that question about the Hilbert space?
Space of states. No, I'm not telling about the Hilbert space. I'm just saying that this picture can be q-deformed, and I have not completed it, but yes, Liouville-Guéry, yeah. So, that is just, so that is what I'll land on this, where this operator is that T. Let me just complete that story. So again, let me just, you can again find out an omega, which is the Casimir of this quantum group, and this operator turns out to be different. I mean, something which lands on this if you take q goes to 1, but others it's slightly different. And I'm going to find the wave functions now. What happens is that now what we should replace is eigenfunctions of B. Now B is not del Z, B is this complicated, not complicated, that's some discrete operator. So we want to find the eigenfunctions of that, and that also happens to be a q-deformed exponential. I mean, you just take the exponential, instead of writing z to the power n by n factorial, instead of n factorial, you write some q Pochhammer or something, which generalizes the factorial to q's, and then you do this. Okay, sorry, not q square, q. Okay, and then just proceed. Okay, and let me just write down the answer. Okay, and it turns out that you need to do one more small rewriting. 5 goes like log Yeah. So this is discrete. Now there is nothing. So let's say H sits on a lattice now. Okay, half lattice. Maybe I should say that. Yeah. Sorry. So these ones are Q. These ones are Q. But there are other generators which translate by half lattice. Sorry. What is?
If you're saying that, like I'm looking at a line.
Right.
And what is it? When you say lattice,
Like he's giving one Q.
Yeah. So instead of taking H to be, for example, a real line, what you take is that Q square, Q cube, or maybe even Q to the power minus 1. This is what I mean. Yeah. And your generators only take you between these lattice points. That's what I mean. Yeah. It's consistent to truncate. Small n is any number here. Yeah, just denoting lattice. H can take values in Q to the power n by 2. Sorry. 3 by 2 and so on. Yeah. So you can just continue this story, and as I was telling you, H can be written as Q to the power minus n by 2. And then I can write a discrete operator in n. So let me write it down. Okay, and again, you also need an un. Maybe I can even call it Vn so that it looks similar to what we had before. Vn is Q to the power minus n by 2, some Pochhammers. These details are not very important because I'm not giving you the details. And something like this. So this is a way of giving from the H to the n lattice. And then if you write down omega dot V is equal to some number times V, or omega dot V is this Vn minus 1 plus 1 minus Q to the power n plus 1. Vn is equal to some number times Vn n plus 1. Sorry. No, this is more related to that other T operator that I wrote, T tilde operator that I wrote, where it was 1 on the below diagonal and 1 minus Q to the power n on the off diagonal side. Yeah. So let me just, I'll just stop here.
What does this mean? Sorry, that's very nice. You got this equation,
right?
This expression, which is the same as the one you derived by this.
All right.
Now, then you went over into this that set space, geometry, whatever. And what does this say about the Hilbert space in the system?
I think it doesn't say anything about the Hilbert space for now. I mean the bulk, you mean the bulk Hilbert space.
You're reconstructing the bulk in some way.
Okay.
What can I say about the states of the system?
I think the states are okay. I mean, we had these states, right? I mean, these are the Hilbert space. These are the states. This, I mean, that's. You mean some bulk interpretation?
You're saying that you have some double scale SYK which has a partition function.
Yes.
And the statement is that there is some quantum version of a cosine.
Yes.
Q-deformed cosine.
Yes.
On which you have some natural, functions living on that.
Yes.
Functions
yes.
on that.
Yes.
And somehow, those sets of functions, there's a one-to-one mapping between those guys and the eigenfunctions of this effective family.
Yes. That's practically true. Now, yeah, that's true. So
effectively, the effective states that appear in this partition function can be thought of as some fields living on some non-commutative.
Yeah, I think that's true.
Okay, which is defined by this q-deformed cosine.
Yes.
That,
yes, that's true.
And somehow, if you take q goes to one limit, you remove the q-deformation. Then this becomes Liouville-like.
Liouville-like, yeah.
Which is the SYK.
Which is the SYK.
Standard SYK.
Yeah. So
then it becomes geometric.
I mean, what I would like to make, I mean, I'm not making that, but what would be an ideal thing? We are not, is that we are going to say that this ADS, this is the bulk. Okay, now this is 3. I mean, this is 3-dimensional ADS3. It's not ADS2 yet, but you can kind of stop halfway here in this procedure. I mean, you only do reduction on the Z side, but not to the Z bar side. That gives you some kind of ADS2.
Are you saying that you project to be equal to 0 or something?
Right, that is one way of saying it. Yeah. You focus on the mu bar equal to 0 subsector of the this wave functions.
So that becomes
that becomes an ADS2. What we would like to say that's the bulk dual, but of course that's not what we're saying. In the sense that would be very nice to have. But yeah.
So the statement is that the full spectrum, larger in this double scale, not just the Schwarzian, is actually described by functions living on this q-deformed.
Functions living on this q-deformed space.
Yeah. And somehow, like this q-deformation goes away when you take the SYK element to the standard SYK.
Right.
And then you want to say there's something living on this.
Yeah, that is after you remove. But even with the presence of q-deformation, whatever role that ADS2 played in the usual SYK story,
there's a q-deformed.
There is a q-deformed version of it. That's.
But this raises one important question. That if you consider finite temperature SYK mass, it describes a black hole in the bulk. That we know. Explicitly, we can do all this. So this would raise a very important question actually about what happens to that statement. Black holes have horizons, SL2R, all that sort of stuff. So this is some non-perturbative quantum gravity, some non-commutative geometry. These are all words, but these words seem to be coming over from the blackboard.
I mean, there is no temperature here.
I'm saying put in the temperature.
But you have a full spectrum.
But the full spectrum. Yeah, full spectrum.
You're complaining that you can't calculate the partition function also. You can't do the sum. But there is some temperature in this model. There is no that is from the beginning point, starting point. There's not, it's a fermionic model. You can put a temperature. It's a finite Hilbert space. Can't be like any. That is a finite engine itself.
But there is no. I mean, this is already the temperature, finite temperature answer, right? This is already the finite temperature answer. That Hamiltonian, you compute e power minus beta h of that. That's it.
Yes, that's true.
So there is nothing more to do about finite temperature. It's already finite temperature.
Trying to understand the implications for the bulk precisely connected to the question of black holes for which is so frequently. I mean, you have some sort of a non-commutative geometry in the bulk.
Yeah, that's what this is saying. But this is, I mean.
So the limit of which would be, the standard Riemannian type of geometry on which SL2R acts, etc. So I'm just trying to understand what does the horizon lift do in this type of model? That would be an interesting question.
Yeah, all this ADS2 business, everything is discrete. I'm sorry, topological.
Metric is not clear.
Yeah, there is no metric here.
Probably there might be some
way of writing,
some commutative way of writing.
Yeah, that's possible. Like there is this Mayol product kind of thing that you can do. Take commutative coordinates, but then the functions, products of functions are something non-trivial. That is another picture that we have not looked at. Yeah. So this is 1 second. Just let me stop with some comments. Okay, what is not precise in what we have done? So what is not precise is that there are some ambiguities here, in the sense that I told you that there are some quantum groups with some parameters. I think these parameters are well understood. But here, some parameters here, there is no systematic classification of all possible cosets. So we have picked up in some math literature, something here, but we don't know whether that's the full story. And if that is not the case, then you'll have to, argue why this is, why should you look at one particular.
I didn't understand why you moved to SL2C. It would have been more natural to think of a coset of SL2R mod U1.
Right. It's actually SU1, maybe. Yeah.
SU1, mod U1.
Right.
Wouldn't that be more natural? It would give you an ADS2 type of thing, and many similar things would happen for that.
Right. That's true. But we've not been able to find one. We spent some time looking around for quantum deformations of SU1, and then coset spaces built out of it, but we could not find.
You mean you could not find in the mathematical literature
yes.
something, but I'm sure it exists. I think the q-deformed SU1, I think exists.
Yeah, that is there, but that is not enough. You need to do this whole procedure. I mean, this coset space, you need all the way down to the coset space.
Sure, but then U1 also, I think you would, I mean, this sounds like a more complex version of that, because you could imagine sort of restricting to a U1 in S.
Yeah.
So instead of that, you would
directly
land on the SL2.
Actually, that was our first thing.
And there was an ulterior reason for me to also ask this, because I think the SL2R mod U1 coset, I think would be the natural home for other reasons I can think of. But having to do again with the q goes to 0 limit. But I don't know, is there a simplification?
It's not SL2R. That's we kind of know it because I was telling about
SU1, yeah. I mean, that's some, there's some real form, whatever.
Sure. But the quantum deformations are totally different.
Okay. But yeah, I think SU1, would be fine as far as I'm concerned. But no, I was wondering, is there a simplification in the q goes to 0 limit again? I mean, that limit, it becomes a little degenerate, no? Your lattice and all that.
Yes. Right.
But is there a way to scale it out or something which makes it somehow simpler? And I mean, because there are two interesting limits, the q equals to 1, which is the undeformed limit, and then there's a q equals to 0 limit. I was wondering, q equals to 1 is the undeformed theory, and the q equals to 0 is the opposite limit, which I think is also interesting. Is there a way you can maybe simplify in that limit by taking some appropriate scaling and so on?
Yeah, we have not thought about it. That's But that's probably true. I mean, certainly commutation relations and all becomes much simpler, but the lattice, I'm worried about what to do with the lattice.
And by the way, this construction that this is somewhat different from what Douglas Stanford has been doing. Douglas Stanford had, I think he has a paper maybe, but he gave a talk, which I heard, in which he talked about the q-deformed SL2. It's probably related to this two-sided Hilbert space that you were talking about, and he was having this construction. This is not the same as that.
No, two-sided is definitely different, I would say. They have a different way of thinking about it, but I don't remember whether Stanford has written a paper.
He may not have written a paper, but you can check out the Santa Barbara webpage. KITP, he gave a talk in February.
This February, okay.
January, February, yeah.
I'll take a look at it, yeah. Just one thing, let me say what I'm not doing. I mean, that would be nice to do, but we have not been able to do it. But for example, you start from ADS2 and then go to the boundary and then to JT gravity or Liouville theory. That would be the ideal situation. Like you start with this non-commutative ADS2, which takes this non-commutative ADS2 and then figure out a way to find the effective theory for it. That would be very nice, but that's not what we are doing. That turns out to be too complicated. We don't even know what's a quantum gravity. I mean, how to even formulate an integral, an action. We tried, but we couldn't. So that's not what we are able to do. Yeah, this is the best that we could get.
In all the states, you might want to get some non-commutative string here. You're just taking a larger limit, but you're finding an arbitrary lambda. So there's almost like a non-commutative string.
Even let's say you don't want to do all the way full non-commutative. Let's say q goes to 1, but systematic corrections to it. That one should be able to do, I guess, in some sense. But that also we are not being able to do.
Maybe easier at a given q then q goes to 1. See, it's a bit like, like trying to get the full string spectrum versus, trying to get curvature corrections in the, in a supergravity. Okay, now,
I would think that's easier, right?
Well, curvature correction supergravity is, like there are many curvature corrections possible, right? And string theory chooses one of them.
Yeah.
But if you have all the string states, it is pretty unique. There's a very strong mathematical structure which is constrained.
Yeah, but we don't even know.
Think of it as, like just gravity and correcting it. Okay, that you are kind of, like there's a very wide space within which you are trying to find out something. Okay, where like you have not implemented. Whereas, but
this suggests something concrete, right? In the sense that.
Sure. So actually, I wanted to ask another thing. Like like does something happen if you I understand that if q has some particular meaning and so on. But let's say if you take q to be some, let's say, square root of unity.
Yeah, that's a different story. Yeah.
So then, which basically means q to the power p is 1. Okay, so you put some condition that not that this p, but some other p. If p is 1. Okay. So then like at least there are these these periodic string theories and so on, and periodic CFT. People have thought about where like things like that appear. Okay. So I was wondering whether you can just analytically continue this story to some square root of unity, where you can where the dual theory you can say is periodic. So there also what happens is that on the bulk is you basically get some graph, some discrete thing, okay, some logarithmic scheme. So from the graph, okay, on which things live, and some very natural periodic string theory which lives on that. Okay. So I was wondering whether like you could analytically continue this story somehow, somewhere to kind of be in contact with that story.
Yeah, I don't know. Yeah, I don't know.
Because that would be good, because the periodic string theory story is mostly kind of, as far as I understand, it's kind of taking some natural generalization and constructing. There's no actual like boundary theory they have. I mean, it's more like kind of try to do something which gives you something. But if you can say that like, oh well, this what you're getting is some analytic continuation of double scale SYK, that would be something, right? Like, because then you have a more then you have a very specific system, okay, which at least like under some analytic continuation you have. I don't know whether that's possible.
Yeah, I don't know the relation between q-deformed and the periodic cases.
But sometimes I thought you get some things if you take the q to be some square root. You have to do something like that. I mean, you have to. That would take it away because q here is a minus lambda.
Yeah, it's an analytic continuation. I agree to the square root of unity. Definitely in the quantum groups, square root of unity, some root of unity is a very
nice
special
point. So far as the Schwarzian theory, that is a natural.
Correct. So that's what you have for the compact groups. Q-deformed SU2, SU2 level K, you get something like that. You get 2 pi I over K plus 2 or something. I mean, I was listening about the connection to the periodic, which is, I thought, maybe
because here we get something living on 1 q which seems like
it's a circle.
It's a little more crazy. It's not space, but
But here also it's not clear like what is the matrix.
Yeah. Actually, there is one more formulation, I mean, which might have some connections, which is the BF theory kind of formulation. BF theory. So, I mean, so right now the problem is that there is no geometry, but there is a nice group theory. I mean, if you can convert a group theory into a geometry, then you're in business. That's what kind of this happened, that we realized geometry via group theory, and then we know how to deform the group theory story. So this BF theory is a place where you can do group theory, because BF theory based on SL2R is the JT gravity. So you might be able to do BF theory based on some q-deformation of SL2R. There are some, I think Mertens is thinking about those kinds of things. BF theory based on some q-deformation.
That's a 4BF in what?
Huh?
2D also you have a BF.
2D you can do a BF theory. Yeah. Yeah, it's a kind of well known that BF theory and Schwarzian, you can land on the Schwarzian because they're the same as JT gravity. But the essential thing is that SL2 is the SL2 controls everything there. So, but we know what deforms SL2, so maybe
For example, joint orbit of diff.
Right. Yeah. There is a q-deformation of Virasaro is what I've heard.
I understand.
But the question is, all these things are, it sounds natural when we say it, but then practically doing it is a problem because there's a lot of mathematical literature here which we cannot penetrate. We have one of our collaborator is mathematician. I mean, almost mathematician, but still. Yeah. So, for example, some of these things are just not even there even in math literature.
This is all in your recent paper.
Yeah, December. Yeah. For example, there is here. I'm just telling you that these are these q exponentials are there, but there's no completeness relation. There's no Fourier transform available for this. We don't really know what sets of values those mu take. We kind of expect that mu takes discrete values. Again, it's a discrete set like that because it's a Fourier transform of that lattice. But there is no known spectrum, right? So certain things are just missing.
There are no more questions. Let's thank.
Thanks.